We talked about static friction. And you can think of this as providing whatever force is required to prevent sliding up to a maximum value, up to mu sub s times the normal force. And if a bigger force than that is required to prevent sliding, then it'll start to slide. So now we're going on to kinetic friction. This one is easier to deal with. So unlike static friction, kinetic friction is always calculated the same way. You know, there's no trying to figure out what force is required and then comparing it to an answer. Kinetic friction is always calculated the same way. So the force of kinetic friction is equal to the coefficient of kinetic friction. So notice that as a different subscript, but it's still that Greek letter mu. It's still a coefficient of friction, times the normal force. That's the magnitude. And then the direction. Oh, that's right. So it's in a direction. I was afraid that was going to be like a fire drill or something. But I'm like, that must be such a small fire. In a direction opposite the velocity vector. Okay, so it's always trying to slow it down. It's a force that's always acting opposite the velocity vector. So notice you always have to know the direction of motion to calculate kinetic friction. Okay, so let me do an example. So let's say there's a block on a 20-degree incline. And let's say that the coefficient of kinetic friction is equal to, let's make it small, 0.05. What are the units of coefficient of kinetic friction? No units. Both of those coefficients have no units. And you can see that from the equation for the force. The force of friction is in newtons, normal force is in newtons, and so this has to have no units. And let's say that the mass is 10 kilograms. And let's calculate the force of friction vector if at this instant the block is sliding down the incline. And then second, what's the force of friction if the block is sliding up the incline? Before I go into these calculations, okay, so what are the forces acting? There's just a normal force and a weight force. How is B even possible? How could it possibly be sliding up the incline? Yeah, I mean, we know there's no force going up right now, but the velocity doesn't care about the forces happening right now. Velocity only cares about the forces that happened in the past. Okay, and so this is an example where like there was a force that got it moving up the ramp, got it sliding, and then that force disappeared, and that's when we do this analysis. Okay, so if you ever look at a problem and you're like, how could it be going up? There's nothing making it go up. That stuff already happened. Velocity is like sort of a history of past accelerations. I like that. That's like science fiction-y sounding. Okay, so part A, free body diagram. There's a weight force of 98.1, and there's a normal force, and now there's a friction force. And which way does the friction force go? It goes up the ramp because it's always opposite the direction of the velocity vector. And since it always has the same magnitude, I can write this as, I can just put this in here like this. Okay, we don't have to like calculate what it needs to be and then calculate this and compare to it. That's just what it is if it's moving. And we're going to use the rotated coordinate system because all things considered, it makes these problems a lot easier. The only, yes. It's times the normal. And the way you can tell when I write it is when I mean the normal force, I'm always going to give it the hat and shoes. And when I mean it as newtons, it'll always just be a plain capital N. That is a real pain. Okay, so the only thing that we have to figure out components for using cosine and sine is the weight force. So let's figure out what that is first. Once we get that for part A, that won't change for part B. So that's good. Okay, so here's X, here's Y. The weight force is this way. Whatever the angle is with the horizontal, that's the angle between the weight force and the negative y-axis. So we know that this angle is 20 degrees. This is the theta we want. And in this configuration, it's 270 to get to the negative y-axis, and then we have to go 20 more. So this is 290. So that weight force is 98.1 times cosine of 290, 98.1 times sine of 290. Can someone tell me what those are? Okay. Okay. So now Newton's second law, we have the weight force. And the normal force is always just 0 n. The friction force is always has only an x component, but it can change signs. In this case, that's in the negative x direction. So that's negative 0.05 n, 0 for y. That's all the forces. And then this is equal to 10 times the acceleration, which is only in the x direction. Well, in problems like this in the past, we've just skipped calculating the normal force because we haven't been asked for it, and these problems usually don't ask for it. With friction, since you need that n to figure out what the friction force is, we have to use the y equation first to find n, and then plug that value into the x equation in every one of these problems. Okay, so the y equation says, negative 92.18 plus n is equal to 0. So n is equal to 92.18. And now we'll plug that into the x equation. And we get 33.55 minus 0.05 times 92.18 is equal to 10a. Can someone calculate a for me? Positive 2.894 meters per second squared. And then if you want that as a vector, I'll get back into this acceleration vector. And the acceleration is 2.8940. Or you can also just think of that as a magnitude of 2.894 going down the ramp. Okay, so we did this one with the velocity sliding down the ramp. Is it speeding up or slowing down? Speeding up because the acceleration and velocity are in the same direction. Because V and A are both in that direction. Okay, so now we're going to do it with it's the same configuration, but now we're talking about this block is sliding up and gravity's slowing it down. So what's going to happen here? So free body diagram. There's a weight force of 98.1. There's a normal force N. This time it's sliding up the ramp, so the friction force is down the ramp. And the magnitude is 0.05 N. Newton's second law says, the weight force is the same as it was before, 33.55, negative 92.18. The normal force is 0 n. And the friction force is in the positive x direction this time. because of the direction change of the velocity. And that's equal to the mass times the acceleration. So the y equation says the normal is the same as it was before, 92.18. Plug that into the x equation, and you get 33.55 plus the same friction force we had before, but in the other direction, is equal to 10a. So this time, what do you get for a? 3.82 meters per second squared. And so it's an acceleration down the ramp because it's in the positive x direction. You can write it either of these two ways. Okay, two questions about this. First, is it speeding up or slowing down? It's slowing down because the velocity is this way and the acceleration is this way. And then the second question is, notice, the magnitude of the velocity was the same in A and B. And that's because the normal was the same in both of them. And you calculate that friction force as the coefficient times the normal. So how is it that the acceleration changed? Well, so because even though the magnitude of that friction force is the same, if you change the direction of that friction force, it interacts differently with the other forces. And so in part A, when it's sliding down the ramp, you have the friction force fighting against the weight force. The friction force is acting this way, the weight force is acting this way. Okay, and so you get, sort of because of that fighting against each other, you get a smaller value for the winning acceleration. And the winning one in this case was gravity. But then in the next example, the weight force is pulling it down the hill. The friction force is also trying to pull it down the hill. And so those two effects add and you get a bigger total acceleration. Yeah, that's all. Any questions about that? Okay, let's stop there. So I'll give you some friction problems to work on today. I'd be happy to answer questions about those tomorrow or lab stuff tomorrow. And then when we're done with that, we'll go on to the last type of forces, springs.